So, hello to everyone who's watching on YouTube. I guess we'll wait for a few minutes so that a few students can join the session. So, I'll start in like 5 or 10 minutes so that a few people can join the session in person. So, hello everyone. Since I guess no one else is joining the session, we can get started. So, first of all, just to introduce myself, hello Varad, hello Jyotilal. I'm Lakshya Saggi. I'm the problem solving TA for the Monday 6 to 8 p.m. sessions for the NPTEL Games and Information course. So, I believe there was a slight miscommunication this week. I'm sorry for the confusion cause. So, the sessions are supposed to be from on Monday 6 to 8 p.m., not on Tuesdays. So this week, I think I took the session on Monday, but then a lot of students were joining the session on Tuesdays and they were confused. So this is just a makeup session because a lot of students might have missed the first session because of this confusion. So we'll just be discussing the problems which were discussed on Monday again. So you might have seen the problems already because I uploaded the Monday session anyways on YouTube, but just so that we can have a live interaction, maybe you guys have some doubts that you want to ask in those solutions or something. So that's why we are holding the session again, but we'll be discussing the same problems. So I'll just maybe share my screen so that we can start with the problems. And also while taking these sessions, I'll be assuming that you guys have gone through the lecture materials for the week. So this session is for week one, so I'll be assuming that you guys have already gone through the week one lectures on NPTEL, what are strategies and what is a Nash equilibrium and stuff like that. So yeah, so keeping this in mind, maybe we can get started. I'll just share my screen and yeah. And if there are any technical issues you face, that the screen if the screen is not visible or my audio is not clear, then please let me know via chat so that I'll try to fix that. And also if you have any doubts at any point of time, again feel free to ask the doubt in chat and I'll try to answer it to the best of my capabilities. Okay, so yeah, I hope my screen is visible to everyone. So this so I guess we can get started. So I think we have 8 or 9 problems for the session, and yeah, we'll be discussing these problems one by one. So the first problem, some of the problems are just warm-up problems for us to get comfortable with Nash equilibrium and payoff matrices and stuff like that, which will just be very straightforward questions, but still are necessary for revision. And 1 or 2 questions will be a bit more challenging, which will be in the end. So the first question says that consider a two-player game whose payoff matrix is given by something like this. So we know that there is this row player which has strategies T and B, and there's this column player P2 which has strategies L, M, and R. And we are given the payoff matrices. And what does the payoff matrix denote? The tuple in the payoff matrix, the first entry denotes the payoff for the row player, and the second entry denotes the payoff for the column player. And now, yeah. So if row player plays T and column player plays L, then that means row player gets a payoff of 1, whereas column player gets a payoff of 0. And note that since this is what are we calling a payoff, usually everyone wants to maximize their payoff. So row player will want to maximize his payoff. Column player will also want to maximize his payoff. So these are the bunch of strategies which are given to us, and then we have to select the correct options. So what's the option A? Option A says that for column player, strategy M dominates strategy R. So let us see these strategies M and R, and let's see if there is a domination for this. So for the column player, these are the strategies like M and R, and we want to see if one strategy is strictly better always than the other. So let's see if the row player had played T, then column player on start playing M gets a payoff of 2. Whereas on playing R, the column player gets a payoff of 1. Since 2 is greater than 1, so if row player is playing T, then the strategy M is better for column player. Similarly, if the row player plays B, then if column player plays M, then the column player gets a payoff of 1. Whereas on playing R, the column player gets a payoff of 0. So what does this mean? This means that irrespective of whatever the row player plays, the strategy M is always giving a better payoff for column player. The column player's payoffs are by the second entries. So for this row T also this 2 is greater than this 1, and for this B row also this 1 is greater than this 0. So yeah, so for column player the strategy M actually is dominating the strategy R. So at least this option is correct. And then the second option is for role player strategy. Okay, so maybe I also have the solutions typed out for these. Maybe I should just put them into a notice. So yeah. So the first option at least says that like uh, like case one is just if player one the role player plays T, then payoff for this is just like I've just written down this whatever I was just going to say here. That whatever I was just saying, this is just written and like we can see that strategy M dominates strategy R. But for role player here, the second statement says that for role player strategy M dominates strategy R. But note that there are no strategies M and R for the role player. The role player strategies are just T and B. So yeah, yeah. So as Bharat also pointed out in chat that M is a dominating strategy for column player. Yeah, Bharat, like you were correct for this option. And now we are in this B option, and in this B option, we are saying that for row player strategy M dominate strategy R. But note that for row player the strategies are only T and B. There are no strategies like M and R for the row player. So there is no notion of a strategy, like of a dominating strategy for the row player, as M and R are not even the strategies for the player. So this statement is incorrect as M and R are not the strategies for the row player. Similarly, what about C option? C option says that for column player strategy, T dominates strategy B. Is this option correct or is this incorrect? This option, like the C option for column player strategy, T dominates strategy B. What do you think, like Varad or Jyotilal? Okay, so Varad is saying that C is incorrect. So yes, Varad, so actually you're correct. So good job. Again, like in the B option, we said that for role player M dominates R, but M and R are not even the strategies for the role player. Similarly, in C option, we are talking about strategies T and B for the column player. But note that these are not the strategies for the column player, these are for the row player. So this does not make any sense anyways. Because for these are not T and B are not strategies for column player, they are the strategies for row player. So C option is also incorrect. Now coming to the D option, the D option says that for row player, strategy T dominates strategy B. So like for row player, we have the strategy T and B, and now we have to figure out whether strategy T is dominating strategy B or not. So any guesses or or does anyone want to answer this in chat? Okay, so Varad is saying that strategy T indeed dominates strategy B. Okay, maybe like I don't remember the answer, so maybe we can just check this. So for row players, so these are the two strategies which we want to compare, and note that for row player, the payoffs are given by the first entries of these tuples. So let's see if the column player has played L, then if row player has played T, then it's strictly better than the what row player gets on playing B because one is greater than zero. So as long as column player is playing L, like T dominates B, but like we have to check for all possibilities, right? If the column player plays M, then what happens if row player plays T, then he gets a payoff of zero, and on playing B, the row player get okay, on playing T, the row player gets a payoff of one, and on playing B gets a payoff of zero. So again, one is greater than zero. So again, we can say that in this case also T is a better choice than B. But if the column player has played the strategy R, then what happens? Then if the row player plays T, then he gets a payoff of zero. But on playing B, he gets a payoff of two. So in this case, like B is a better strategy than T if the column player has played R. So that's why uh, this is not a dominating strategy. T is not a dominating strategy for row player. Because what do you mean by dominating strategy? Like whatever, like irrespective of whatever the column player plays, T should always be, if T was always a better strategy than B, then only it would have been a dominating strategy. But here we can see that if column player played R, then B was a better strategy than T. So that's why since 0 is less than 2, that's why T does not dominate B. So this option would be incorrect. like as would have been pointed out in the solution also. Like incorrect, because if column player plays R, then row player has higher payoff on playing B over T. Like if column player plays R, then row player has a higher payoff on playing B over T. So, well, does this make sense? You said that T is a dominating strategy, but does this make sense? Why is T not a dominating strategy over B? Okay, you got it. Nice. So if you have any doubts at any point, like just feel free to ask me. So yeah. So for this option, like for this question, only option A was correct. Like only the for column player strategy and dominant strategy are other options were incorrect. Okay, then let's move on to the second question in that case. So what does the second question say? Second question says that the order of removal of weakly dominated strategies of each player determines which Nash equilibria are lost. So is this statement true or false? So I hope you guys remember like what is a weakly dominated strategy and what's a strongly dominated strategy. So in weak domination, like equalities can also occur, whereas in strong domination, like it should always be a strictly greater than or less than sign. Like I'm not getting the full definition, but the high level idea is something like this. And the problem is asking the order of removal of weakly dominated strategies for each player determines which Nash equilibria are lost. Is this statement true or false? So any guesses or any ideas? Or what do you guys think? Like, is this statement the order? So note that like obviously like there can be more than one Nash equilibria. I think this has been covered in the lectures that there can be more than one Nash equilibria in a two-player game, right? Like in any game. And now like on removing weakly dominated strategies, we can, and it may be possible that we might remove some Nash equilibria. And now like the Nash equilibria which are lost depend on the weakly dominated strategy which we are removing. Okay, so actually so Varad is saying that it's false, but I think this statement is true. Varad, maybe I'll discuss this also. Like I'll also discuss this. Like this was, I believe, uh, this is something which has been actually discussed in the lectures also. Like exactly this statement was discussed in the lecture. So yeah, but I'll just try to like repeat the argument whatever was discussed in the lectures here also, so that if it was not clear in the lecture videos, then hopefully it becomes clear this time. So actually, this statement is true that order of removal of weakly dominated strategies determines which Nash equilibria are lost. And now, like I also have an example prepared. Maybe we can see in the example step by step. Okay. So suppose so suppose this is the payoff matrix which is given to us. So where column player has strategies L, C, and R, and the row player has the strategies T, M, and B. So there are three strategies for the column player and three strategies for the row player. Like, okay, why are these named L, C, and R? Like this can you can just think of it as left column, the center column, and the right column, and these are like top, middle, and bottom rows. Just like in short, these strategies have been written as this like TMB and LCR. And let's suppose this is the payoff matrix given to us. Okay, so now like let's see like okay, while finding Nash equilibrium or just while removing like while finding out any weakly dominated strategies. So would it some any of you like Jyotilal or where would you like to guess like are there any weakly dominating strategies present here? Like maybe you can just try to answer it if there is any, like and point out like if there is a weakly dominant strategy in this payoff matrix. Like if we are talking about like domination with respect to the row strategies, then you have to look at the first entries of the tuples. And while discussing about the column strategies, you have to look at the second entries of these tuples. Just making that clear, okay? So any guesses, guys? Like Maybe you can just try to guess and we'll see whether it is or is it not a weekly dominating strategy. Like in this pair of matrix, does there exist any weekly dominating strategy? And if so, that can you give the example of that strategy? Okay, maybe we can see this directly. So yeah, I should just put all of this on the second page. Hmm. So let's see the case one. So okay, like there are multiple weekly dominating strategies. Let us look at one. So what I'm claiming is the strategy M is weekly dominating the strategy T. And why is this the case? Like you can see that this is the strategy T and this is the strategy M. Let us see these two strategies. So these are the strategies for the row player. So we'll have to compare while discussing the domination with respect to these two strategies. We'll have to compare the first values of the tuples. So if the column player has played L, then see that on playing M we get a payoff of 2 and on playing T we get a payoff of 1. Since 2 is greater than 1, so M is a better strategy than T. Similarly, if the column player plays C, then the payoff on playing M and T are equal. So the strategy M is like no worse off than the strategy T. And similarly, if the column player plays R, then M on playing M we get a payoff of 3, and on playing T we get a payoff of 0. Since 3 is greater than 0, like again, like M is a better strategy than T if the column player plays R. So with respect to all the three columns, like whatever the column player plays, M is not a worse off strategy than the strategy T, right? Because like in all cases, like M is the payoff on playing M is no worse off than the payoff on playing T. So now since I hope like this is clear, like if this, I'll assume like everything is clear if you guys don't stop me in chat. So since M is like always better off than like the strategy, so we can say that M is a weakly dominating strategy. And since M is a weakly dominating strategy over the strategy T, like we can like remove T from the payoff matrix. Like this might remove some of the Nash equilibria, but still like this theorem was discussed in the class also. Like on removing a weakly dominating strategy, whatever is left, if we obtain a Nash equilibria for that game, then it is a Nash equilibria for the original game also, and something like that. So to obtain the Nash equilibria, to obtain one of the Nash equilibria, what we can do is maybe just remove this row. So the payoff matrix on removal of T, because T is being weakly dominated by M. So what we are left is this matrix where we have these three columns and we have removed the strategy T. So there are these M and B strategies for the row player now. And this is the payoff matrix which is left. Like I just removed this row and this is the remaining payoff matrix. And in this payoff matrix, what we can see is actually the strategy L is weakly dominating the strategy R. Like, here we can see that the strategies for the column players. Like you can identify maybe multiple like weakly dominating strategies, but this is just an example. I'm just taking out an example. And why am I doing all of this? Like first of all, I hope the high level idea is clear. So what I'll try to show is the question was asking that the order of removal of weakly dominated strategies determines which Nash equilibria are lost. And I'll try to prove this statement. So what I'll be doing is I'll be removing these weakly dominating strategies in different orders. So I'll be removing different weakly dominating strategies. And then like I'll be saying that on removing one set of weakly dominating strategies, I get one Nash equilibria. And on removing another set of weakly dominating strategies, I get some other Nash equilibria. So this means that the order in which we remove the weakly dominating strategies is actually changing the Nash equilibria which we obtain at the end. Okay, so here what we said was the strategy L is weakly dominating strategy R. And why is this the case? This is the case because in this matrix, let's see just like the strategies L and strategies R. So if the role player has played M, then on playing L, okay, so we are talking about the column player, so we'll be looking at the second entries of the tuples, right? So if the row player plays M and the column player plays L, the payoff is 2. Whereas on playing R, again the payoff is 2. So if the row player has played M, then L is no worse off than R. Like playing L is no worse off than playing R. But if the row player plays B, then on playing L, column player gets a payoff of 1. On playing R, column player gets a payoff of 0. So since 1 is greater than 0, so if the row player has played B, then L is a strictly better strategy than R. So in both the cases, like you can at least say that uh, L is not worse off than R. At least we know this, that L is not a worse off strategy than the strategy R. Whatever the role player is playing, whether role player plays M or B, L is no worse off or playing L than playing R. And what this means is again like since L is weakly dominating R, let's just remove this strategy R from our payoff matrix. And now the payoff matrix looks like this. The the only L and C are left, and here only M and B are left. And here actually you can see in this 2 cross 2 matrix like what are the Nash equilibria. So M comma L and B comma L will be the Nash equilibria for this payoff matrix. And how can we see this? Like we can just check for all these 4 strategies. Like let's see if M comma L is indeed a Nash equilibria. So let's see if ML is a Nash equilibria or not. So on if the row player plays M and if the column player plays L, then both get a payoff of 2. Now let's see like does the row player have an incentive to switch to B or not? So let's see like if the row player like if the column player is still playing L and like if row player switches from M to B, initially row player had a payoff of 2, but on switching to B, the row player will still have a payoff of 2. So row player has no real incentive, like the row player is not profiting on switching. So that's why we can say that row player has no incentive to switch. And so like this M comma L, like row player will not switch at least. Like row player has no incentive to switch from this M comma L strategy. And now let's see if column player has an incentive to switch or not. So what does this mean? So let's see like if the column player like switches from L to C while the row player is still playing M, then we arrive at this kind of solution. So this will be the payoffs. But let's see, initially the column player was getting a payoff of 2 on this M comma L. But on switching, the column player will be getting a payoff of only 1. So the payoff will be actually reduced for the column player if the column player decides to switch. So again, the column player also has no real incentive to switch. So that's why this 2 comma 2, this M comma L is a Nash equilibria. Now let's check for this M comma C, like this entry. Is this a Nash equilibria or this not a Nash equilibria? So let's see, like let's check for the row player if the row player has an incentive to switch or not. So in if in this M comma C, the payoff for the row player is 2 and the column player's payoff is 1. So if the row player decides to switch from M to B, then we will arrive at something like these payoffs, where the payoff which row player will be getting is equal to 0. So initially row player was getting a payoff of 2, but on switching gets a payoff of 0. And so row player will not want to reduce its payoff, it wants to maximize. So row player has no incentive to switch from the strategy M comma C. But for the column player, let's see for the column player's current payoff is equal to 1. But if the column player decides to switch from C to L, then the column player's payoff will increase to 2. So actually column player will have an incentive to switch here. So that's why this M comma C will not be a Nash equilibria because column player will have an incentive to switch. Now let's check for this B comma L. Like, is this a Nash equilibria or not? So let's just consider the row player right now. So for row player, the current payoff is 2. But if row player switches from B to M, then the payoff still remains equal to 2 for the row player. So role player has no real incentive to switch because the payoff remains the same. Whereas for the column player is if the column player decides to switch from the strategy, its initial payoff is 1. But if column player decides to switch, the column player gets a payoff of 0. And since 1 is greater than 0, so like column player will be incurring a loss if he switches. So column player again has no real incentive to switch from this. So neither row player nor the column player have an incentive to switch from this entry. So B comma L is also a Nash equilibria. And now let's just check for the last part also, this B comma C part, if any player has an incentive to switch or not. So in this, you can actually see that both the row players as well as column players are getting a payoff of 0. And if the row player decides to switch, then this payoff increases to 2. And if column player decides to switch, the payoff increases from 0 to 1. So actually here both the players are having an incentive to switch. So this is also not a Nash equilibria. So both of these M comma C and B comma C, both of these are not Nash equilibria, and ML and BL are actually Nash equilibria. So note that this says that, so what we have arrived at is ML and BL are Nash equilibria for this game. And how did we arrive at this payoff matrix? We arrived at it by removing some of the weakly dominating strategies from the initial matrix, which was this matrix. So actually this means that ML and BL are Nash equilibria for the original game also. So for this game, ML and BL are like these two are actually Nash equilibria. And now we'll see, okay, so these two Nash equilibria, we arrived at these two Nash equilibria, ML and BL, by removing first, like by first seeing that M weakly dominates G, so we removed T, and then L weakly dominates R, so we removed R. So first we removed T and then we removed R. And using this, we actually arrived at one Nash equilibrium. Like we arrived at two possible Nash equilibria, which are ML and BL. But uh, but let's see, like if there is another order in which if we like remove the rows, the weakly dominated like strategies, then will we be getting a different Nash equilibria? Okay, so let's again just keep this matrix in mind. This was the original payoff matrix. And in case two, what will like now we'll be removing a different set of weakly dominated strategies from the initial matrix. So first we observe that M weakly dominates B. Like let's just forget about this case one part. This was one way of removing the weakly dominated strategies. Now we'll say that there is another ordering on removing those strategies, like we'll be obtaining some different Nash equilibria. So this is the case 2, and in this case 2, uh, we'll say that M actually weakly dominates the strategy B. And why is this the case? Let us look at the original matrix and let's see the strategies M and B. Like our claim is that M weakly dominates strategy B, and we can just check this like okay, so M and B are the strategies for the row player. So for the row player, we can have something like 1 second, guys. Yeah. So M and B are the strategies for the row players, and for the row player, like the first entries of the tuples will correspond to the payoffs for the row player. So let's see. If the column player played L, then M is the payoff on playing both M and B is equal to 2. So M is no worse off than playing B in this case. But if the column player played C, then payoff on playing M is actually equal to 2, whereas payoff on playing B is 0. Since 2 is greater than 0, so if the column player played C, then M is a strictly better strategy than B. Similarly, if column player played R, then if row player played M, he gets a payoff of 3, and on playing B, gets a payoff of 1. So what this means is that again, if the column player played R, then again like M is a strictly better strategy than B. So this means that like whatever the column player plays L, C, or R, in all three cases, playing M is no worse off than like playing B. So I hope this makes sense. And this is why like strategy M is actually weakly dominating the strategy B. So what we can do, like from the initial game, like we know that M weakly dominates strategy B. So we can actually remove this weakly dominated strategy B just to simplify our game. And this is what we'll be doing in case two. So payoff matrix on remove, then if we just remove the row B from the initial payoff matrix, the 3 cross 3 matrix, like we will get something like this kind of payoff matrix. And now again, like we'll try to remove some weakly dominant strategies to obtain some Nash equilibria. Okay, so here in this payoff matrix, what will be what I'll be saying is what I'll be claiming is the strategy R actually weakly dominates the strategy C. So let's just see like how does this hold like between this R and C. So these are the strategies for the column player. So for the column player, what we actually want to see is so for the column player, what we actually want to see is the second entries of the tuples. So let's see, like if row player played the strategy T, then playing on playing R, he get a payoff of 3, and on playing C, also column player gets a payoff of 3. So the strategy R is no worse off than strategy C if the row player played T. But if the row player played M, then you can see that on playing C, the payoff is 1. But if on playing R, the payoff is 2. So in this case, like R is a strictly better strategy than C. So over both these cases, like D and M, we can conclude that the strategy R is no worse off than the strategy C. And that's why we see that the strategy R weakly dominates the strategy C. And so now we can like actually remove the strategy C from the payoff matrix. And then the payoff matrix will only have these P and M rows and L and R columns. And so now the payoff matrix will look something like this. I have simplified the payoff matrix. Here is the updated payoff matrix. And now we'll see like what are the Nash equilibria in this payoff matrix. And then here, like maybe we can just see entry by entry. Like I have written what the Nash equilibria will be, but let's just see these entry by entry. Like if there is a Nash equilibrium, what are the actual Nash equilibria? So let's see, let's see if this T comma L, this 1 comma 2 is a Nash equilibria or not. So that so like here we'll check like if any of the players has any incentive to switch or not. So right now the row player has a payoff of 1 and column player has a payoff of 2 if we are checking for the entries T comma N. So now if row player decides to switch from T to M, then the payoff of row player increases from 1 to 2. And so like row player will have an incentive to switch. So that's why like T comma L will not be a Nash equilibria because row player will always have an incentive to switch for a better payoff. So T comma L is not a Nash equilibria. Similarly, let's check for T comma R. Is this a Nash equilibria or not? Again, the row player's payoff is 0, column player's payoff is 3. But if the row player decides to switch from T to M, the payoff of row player increases from 0 to 3. So again, row player will have an incentive to switch because his payoff will increase from 0 to 3. So again, this T comma R is not a Nash equilibria. And now let's look at this third case, the M comma L case. Well, actually, we arrived at M comma L is a Nash equilibria previously also, like in the case one, but let's just look at it again in this payoff matrix. So right now, if we are checking for M comma L, the payoff for both row and column players right now is a 2. But now if row player decides to switch, the payoff decreases from 2 to 1. So row player will have no real incentive to switch. And let's check for the column player. So column player's payoff right now is 2. But if column player decides to switch from L to R, uh, the payoff for the column player remains a 2. Like initially also it was a 2. And if he switches, the payoff is again a 2. So again, column player also has no real incentive to switch. Column player will not profit from switching. So that's why we can say that M comma L is a Nash equilibria because neither of the two players, row player or column player, want to switch. So M comma L is a Nash equilibria. And now let's check for this M comma R, if this is the Nash equilibria or not. So right now, row player the payoff for row player is 3 and payoff for column player is 2. So if the row player decides to switch, then the payoff for row player will decrease from 3 to 0. So row player will have no real incentive to switch. Whereas for the column player, if the column player decides to switch from R to L, then the payoff for column player is earlier 2, and after switching also it remains 2. So again, the column player has no real incentive to switch because like column player is not profiting. So that's why this 3 comma 2 is also an Nash equilibria. This M comma R is also an Nash equilibria. Okay. So we arrived at this M comma L and M comma R are Nash equilibria for this game. And since at this game we arrive by removing some weakly dominant strategies. So this means that ML and MR are actually Nash equilibria for the original game also. Okay. So note that we arrived at this Nash equilibria by first like removing B and then removing C. Like all of these were like weakly dominated strategies, so we could remove them. So first we remove B and then we remove C, and that's how we arrived at this Nash equilibria. But on the other hand, in the case one, on removing T and then on removing R, we arrived at the Nash equilibria ML and BL. So in one case, we arrived at ML and BL as Nash equilibria, whereas in other case, we arrived at ML and BMR as the Nash equilibria. So what this means is that the order or the actually the weakly dominated strategies which you remove changes the final Nash equilibria which you are getting. Like in the case one, on first removing T and then removing R, you got ML and BL as the Nash equilibria. Whereas if you first remove B and then remove C, you would get ML and MR as the Nash equilibria. So like this MR does not occur in case one, and similarly this BL does not occur in case two. So that's why the order of removing the strategies changes the order of removing the weakly dominated strategies changes the Nash equilibria which we arrive at in finally. Like it can potentially change. It necessarily will not always change, but it can potentially change. But note that like this is only true for like weakly dominated strategies, as was discussed in the lectures, also discussed in the lectures, that you can always like the Nash equilibria don't get affected if you remove strongly dominated strategies. But like Nash equilibria, which you get, can change if you remove weakly dominated strategies. So yeah, and this is an example where the final Nash equilibria actually changes the Nash equilibria which you get actually is different on removing different weakly dominated strategies. Okay, so yeah, so I hope this makes it clear. Like, okay, so Deepak has his hand raised. So Deepak, you can just ask your question in chat. Like, if you have a doubt, you can like straight away type out your doubt in the chat. You don't need to like wait for raising your hand. And so Deepak, if you have questions, like you can type in the chat right now. So Deepak, like, can you say, so Deepak, like LC and R no, don't really have any full form. Like these are just the names of the strategies which we have given. Like, like you could have just call these strategies as like rock, paper, scissors or 1, 2, 3. The name of the strategy does not matter, right? It's just a canonical thing which we have like pasted onto them. So like what I'm saying is, like there is no real like there is no real like what does L mean? There's no real meaning to L, C, or R. These are just arbitrary names. But like why did we name it as such? Like just you can think of these as like since this was the leftmost column, like since this was the leftmost for of the three strategies for the column player, we called it L, like L for left, C for center, and R for right. Similarly, for this TMB, we could just call this as top row, middle row, and bottom row. But these have no real meanings. Like you could have just put A, B, C, and X, Y, Z here, and it still would not matter. Okay, so Darshan is asked. Okay, Okay, so Darshan is also typing something in chat. Okay, so Darshan is asking to explain the case one. Okay, so Darshan, what we were discussing was so initially we were given this 3 cross 3 payoff matrix, and now let's just see like if we identify some pair of strategies where one weakly dominates the other, and then remove the weakly dominated strategy. Let's see where we get at by removing like some strategies. Which national criteria do we get that after removing some strategies? So let's just see so in case one, the first we identify that the strategy M is actually weakly dominating the strategy T. That the strategy M actually weakly dominates the strategy T. And why is this the case? Because like let's just see like these are strategies for the role players. So we can just check like if this strategy actually is dominating the strategy T. And how do we check this? So note that for the row player, the first entry of the tuple correspond to the payoff for the player. So like if the column, so by weak domination, what we mean is that whatever the other player is playing, the strategy M should always be no worse off than strategy T. That's what we mean by weak domination, right? So like if the column player had played L, then the strategy, then on playing M, we get the row player gets a payoff of 2, while playing T gets a payoff of 1. So if column player played L, then M is a better strategy than T. Similarly, if column player had instead played C, then M and then on playing M and T, on both the cases, the payoff is equal to 2. So the strategy M is no worse off than the strategy T if the column player had played C. And similarly, if the column player had instead played R, in that case, the strategy M would have been strictly better than the strategy T. So because the payoff is in M is 3 and in T is 0. So what this means is that over all these three columns, like whatever the column player plays L, C or R, the strategy M is always is no worse off than the strategy T. Because in the first column also like M is better. In the second column, M and T are equal. In the third column, like M is again better. So that's why we can say that M weakly dominates the strategy T. And if this is the case, then we can remove this weakly dominated strategy. So we can remove the T from the payoff matrix, and now the remaining payoff matrix will look something like this. Right, I just removed the strategy T. And now again, what I see is the strategy L actually weakly dominates the strategy R. So between these strategies L and R, let's see, so what I claim is L is actually weakly dominating the strategy R. So I mean to check if this is indeed true. Let's just check this by ourselves. So, so these are the strategies for the column player. So what this means that irrespective of whatever the row player plays, the strategy L should not be worse off than strategy R. This is what weak domination means, right? So if the row player had played the strategy M, then on playing L, the column player gets a payoff of 2 because like in the tuple, the second entry corresponds to the payoff of the column player. While on playing R, again the column player gets a payoff of 2. So the strategy L is no worse off than the strategy R if the row player plays M. But if the row player plays B, then on playing L, the payoff for column player is 1. Whereas on playing R, the payoff for column player is 0. Since 1 is greater than 0, so in this case, the strategy L is strictly better than strategy R if the row player had played B. So if the row player played B, then L was better than R. And if row player played M, then L was actually equal to R. Like it doesn't matter. L and R both are equivalent for the column player. So overall, we can say that the strategy L is no worse off than the strategy R for the column player. And so the strategy L weakly dominates the strategy R. And if weakly dominates the strategy R, you can actually remove this whole like you can remove this strategy R and the remaining payoff matrix will look just this part. So this is the payoff matrix which we'll be left with. And now we can just try to identify the Nash equilibria in this 2 plus 2 pair matrix. And like what I claim is like similar to the case one arguments, you will be able to see that here M, L, and B, comma L will be Nash equilibria. Like, here there can be four possible strategies: ML, MC, BL, and BC. And what I claim is only ML and BL will be Nash equilibria in this. Like this again, you can check very easily, like you check, like we checked for case two, like we checked in this matrix also. So yeah. So the final idea is like on removing first the strategy T and then strategy R, we arrived at ML and BL as the Nash equilibria. Whereas on removing first B and then C, we arrived at something like ML and MR as the Nash equilibria. So we arrived at different Nash equilibria after removing different insights of weakly dominated strategies. So yeah, and yeah, that's why the problem statement is true. The problem asked is true. So the problem asked if the order of removal of weakly dominated strategies determines which Nash equilibria are lost. True or false. So this statement was true because in one set we saw that one Nash equilibria which was not like was lost in the case one. Similarly, another Nash equilibria was lost in the case two. So yeah. So this statement is true. So, okay, so I hope it made sense. So are there any, so is this clear now, Darshan, or should I try to explain it a bit more? Darshan, is the case one clear to you now? Okay, like I don't see any response from Darshan in the chat, so I'll be assuming that this is clear. Also, if anyone else has any doubts, then you can try. Okay, it's clear. That's nice. So now maybe we can move on to the third question then. And yeah, just a side note, which I like just told you also that if the problem had instead asked about the strongly dominated strategies instead of weakly dominated, then the statement would be false. Because no Nash equilibria are lost on removing strongly dominated strategies. Like if you remove weakly dominated strategies, we just saw some examples where some Nash equilibria were lost. But like you can actually prove that on removing strongly dominated strategies, no Nash equilibria will be lost ever. So yeah, just a side note. Okay, so now maybe we can move on to the third question. So, third question says that consider a game involving two players where the set of strategies of player A is given by A1, A2, A3, A4. So, these are the four strategies for the player A, and these are the four strategies for the player B, B1, B2, B3, B4. And both the players are trying to maximize their payoffs. And now the question asks us to identify some of the Nash equilibria in this game. Okay, so Deepak is asking in the chat that so Deepak is actually all of these sessions are recorded and uploaded on YouTube. Like I believe you guys would have been provided the YouTube link where I upload all these recordings. So like there is a YouTube link on which like all of these sessions are recorded and upload. Like all these sessions are being recorded and they will be uploaded to YouTube. So yeah, you will be having access to these the recorded sessions also. Okay. So yeah. So coming back to this question, yeah. So these are the so we are given four strategies A1, A2, A3, A4 for A, and for player B also we are given the strategies B1, B2, B3, B4. And we have to identify, like we are given the option and we have to identify like if A1, A P4 is a Nash equilibria, A4, P4 is a Nash equilibria, A3, P4 is a Nash equilibria, or none of these. So there can be more than one option correct. would you guys like to try it out yourself? Like from the options A, B, C. So let's just start with option A. Like, is A1 comma B4? So what's A1 comma B4? A1 comma B4 this. Is this an Ash equilibria? Would anyone like to answer or like just guess? Uh, uh, so Deepak, we don't have these live sessions daily. Like these sessions are uh, only on like Monday 6 to 8 p.m. But since there was some issue like this week, like we are having this session on Friday, but these sessions will be weekly, like only on like at least my sessions will always be on Monday 6 to 8 p.m. So yeah, so these sessions won't be every day. These will be just once a week on Monday 6 to 8 p.m. So would anyone like to answer in chat? Like, is this an Nash equilibria or not? This A1 comma B4. Okay. So Deepak is claiming that this is a Nash equilibria. So maybe we'll just let's just check if this is indeed a Nash equilibria. So for the row player, like in this A1 comma B4, the payoff for the row player is 5 and payoff for the column player is 4 right now. Let's see if any player has an incentive to switch. So if the row player decides to switch to, let's say, A2, then his payoff reduces to -2. So row player has no incentive to switch to A2. Similarly, on switching to from A1 to A3, again the row player's payoff reduces by 1. So again, row player has no incentive to switch to A3. Similarly, row player again has no incentive to switch to A4 from A1 because again the payoff reduces from 5 to 4. So row player has no real incentive to switch from this. But let's just see for the column player also, if the column player has an incentive to switch or not. So right now the payoff for column player is 4. If we switches to B3, then the payoff decreases to 3. So no real incentive to switch to B3. Similarly, switching from B4 to B2, the payoff again reduces from 4 to 1. So again, like no incentive to switch. Similarly, from like B4 to B1, again the payoff reduces from 4 to 3 for the column player. So again, column player has no incentive to switch. So yeah, so neither the row player nor the column player have any incentive to switch from this. So yeah, A1 comma B4 is indeed an Nash equilibria. So good job, Deepak. And similarly, like let's see for the option B, A4 comma B4. So A4 comma B4 will be this something like this, 4 comma 4. Is this an Nash equilibria or not? Again, would anyone like to answer this in chat? Okay, so Darshan is claiming that this will be indeed an Nash equilibria. So would anyone else like to answer also? Like, like is is that what Darshan saying correct or not? Like, is this an Nash equilibria or this is this not an Nash equilibria? So actually, Darshan, I think this won't be an Nash equilibria. And why is this the case? So right now, like if in A4 comma B4, the payoff for both row and column players is equal to 4, right? But note that if row player switches from A4 to A1, like if row player switches from A4 to A1, then the payoff for row player increases from 4 to 5. Like initially row player's payoff was 4, but on switching to A1, the row player's payoff will increase to 5. So that's why row player will have an incentive to switch here. And that's why this 4 comma 4 I think won't be an Nash equilibria. Darshan is typing something in the chat. Yes, Darshan. So for rows, the first elements like in these tuples, the first element denotes the payoff for the row player, and the second element denotes the payoff for the column players. So in this A4 comma B4, like the payoff for both row and column player is 4, right? But now if row player decides to switch from A4 to A1, these are the strategies for the row player. If row player was playing inside the strategy A1, then what happens is the row player's payoff, like if row player decides to switch from A4 to A1, then we arrive at this sort of setting, this A1 comma B4, where the payoff for the row player was 5. Earlier it was 4, but if row player switches from A4 to A1, then his payoff becomes 5. So his payoff actually increases. And that's why we will say that like row player will have an incentive to switch. Like row player wants to maximize his profit. So if he was getting a 5 instead of a 4, he will want to take that. So that's why this 4 comma 4 won't be an Nash equilibria, but this 5 comma 4 will be a Nash equilibria. Like okay, so like, let's not talk about 5 comma 4. This was the first, previous option, but yeah, this 4 comma 4 won't be a Nash equilibria. That's what I'm saying. Does this make sense, Darshan? This Darshan is typing something in the chat. So Darshan is saying 4 is compared with A4 row. No, no, Darshan, like I think there's I think you're misunderstanding a bit. So these are the strategies for the row players. A1, A2, A3, A4. These are the strategies. So what this means is that like you don't have to check this across the rows for the row player. Like if row player switches from A4 to A1, what this means is that the row player now arrives at like we arrive at this kind of a strategy profile. The column player is, let's suppose the column player is fixed, like column player is still playing B4. And if the row player had played A4, then we had arrived at this, like the A4 comma B4 strategy profile look, the payoff for that looked like this. But if row player strategy switches from A4 to A1 and column player is still playing A4, then we get this A1 comma B4 as a strategy profile, which corresponds to this cell. Like don't think of like row players, so we'll be moving for the row player across these rows. You don't even need to remember like where you will be moving, like row player will be moving across rows or columns or something. Just think of these are the set of strategies for the row player. These are the row player strategies. These are the column player strategies. And these are the uh, payoffs for the corresponding strategy profiles. So if the strategy profile was A4 comma B4, this was the payoff. But if the strategy profile is A1 comma B4, then the payoff is this. So initially the payoff was this for the row player. Like the payoff was 4. But now, like if row player decides to switch from A4 to A1, where the column player is still playing A4, then we have this 5 comma 4 as the payoff. Note that these are the strategies for the column players because these strategies change the columns, and these are the strategies for the row player because these strategies change the rows. Is this a bit more clear, Sachin, or like should I try to explain this a bit more? Darshan is typing something in the chat. Okay, so I'll try to explain this again, Darshan. So what do we mean by maybe I'll start with a bit more basics. So what do we mean by row players and column players? So these are the strategies, like there is a player A, there is a player B, and what you said is the player B has these possible four strategies: B1, B2, B3, B4, and the player A has these possible four strategies: A1, A2, A3, and A4. And now what we are saying is like, what does this payoff matrix mean? That if the player A plays the strategy A1 and the player B plays the strategy B3, then let's suppose we add this entry. The payoff for the player 1 will be 2 and player 2 will be 3. Like A will get 2 rupees, let's say, and B will get 3 rupees. Basically, similarly, if player A plays the strategy A3 and player B plays the strategy B1, then this will be the corresponding, like the intersection of B1 column and A3 row will be something like this 8 comma 4. So player 1 will get 8 rupees and player B will get 4 rupees. So this is what the payoff matrix denotes. Like whatever be the strategy profile, like so the tuple like A2, like the strategy chosen by A and the strategy chosen by B, that pair denotes a strategy profile, like which has been discussed in the lectures also, right? So this payoff matrix just denotes the payoffs which every player gets for different strategy profiles. So what does this A4 comma B4 strategy profile mean? That A played the strategy A4 and B played the strategy B4. And corresponding to this, from this matrix, we can conclude that the payoff for the payoff for both the players will be 4. But now what we want to check is if the player A wants to switch from this strategy of playing A4 to a different strategy. So the player A has these possible four choices of strategies: A1, A2, A3, A4. And now we have to see if player A wants to switch from A4 to a different strategy. So let's say player A switches to the strategy A1 and like player B strategy remain the same. Like this is what we consider in the Nash equilibrium, that only one player strategy changes at a time. So if player A changes his strategy from A4 to A1 and the player B is still playing the strategy B4, then the payoff matrix will correspond to the A1 row and B4 column. So this entry will correspond to the payoffs for the two players. And here we see that player A is getting 5 rupees and player B is getting 4 rupees. And like earlier player A was only getting 4 rupees and now he gets 5 rupees. So player A will want to switch from A4 to A1. Uh, so the main idea is that these are the strategies for A and these are the strategies for B. And this matrix is just denoting the pairs. Like don't think of it as anything more. Just think of it as the payoffs for the different strategy profile. So if B was still playing B4, then these are the if the player B was playing the strategy B4, then these are the four possible payoffs depending on what the player A is playing. Because B has already played B4. And now out of these four, like if A was playing A4, but if he switches to A1, then he'll have a higher payoff. So I hope I think okay, like I hope this makes sense. Like if it is still not clear, maybe uh you can check out I think the lecture videos. I think in lecture videos also this kind of thing has been explained like very nicely. So if it's not clear, maybe you should also try to check out the lecture video session. But I hope like a bit of it is clear. Okay, so maybe we can move on with this question. So the like A1 comma B4 is a Nash equilibrium, but A4 comma B4 is not. Similarly, like we can check for A3 comma B1 also. Like maybe I'll just see the answer. Yeah, actually, like in option C also, like A3, B1, we'll also see that is a Nash equilibria. Like maybe we can skip this one, or like you can check this later yourself. Like yeah, that A3, B1 is also a Nash equilibria. So yeah, and so like for this option only options A and C will be correct. Also note that like these same problems, like these same problems, like I had also discussed on Monday 6 to 8 p.m. sessions, whose recording has already been uploaded to YouTube. So like if you want to revisit, like if you want to see this question, like why was this A3, B1 an Nash equilibria, or why was it not, like you can just go to YouTube and see that recording also. So I'll be uploading today's session also, but like so basically for this set of problems, like this set of problems, there will be basically two sessions uploaded on YouTube, and like yeah, one because of the Monday 6 to 8 p.m. and second because of today Friday 6 to 8 p.m. So yeah, so you can like just see, like I guess if you get confused on something in one session, then you can refer to the other session, and maybe in the other session I have explained it better. So yeah, okay. So yeah, I think maybe what kind of, yeah, maybe we can skip this fourth question for now. Like again, like what I'm saying is like these questions have already been discussed, so like you will have like like I have discussed all of these solutions in the previous Monday 6 to 8 p.m. session, so you can access the recording and see this. How did we solve this question in the in that recording? But maybe since we are lacking behind time, like we have to close in like 30-40 minutes. So for now, maybe we can skip this question, and if we have time, we'll come back to it. For now, let's go to the other questions. So yeah. So let's say let's just consider the fifth question right now. So in the fifth question, the problem statement is consider a two-player game given by the pair of matrix this. So we are given a pair of matrix where like yeah, we are given a 2 cross 2 pair of matrix. So for player one and player they are like two possible strategies for each of these players. And now what we want to find out is we want to calculate the final payoff by iterated elimination of strictly dominated strategies. If the process does not reduce to a single pair of strategy, then mention so. So what the problem is asking us is, okay, like we know that we can like check for each of these entries to see if it is a Nash equilibrium or not. But what we just want to check is like, if you find a strictly dominated strategy, then just remove it. And like, if we iteratively keep removing the strictly dominated strategies, if we find such strategies and we keep removing them, then we will be left with like just a single entry, right? Like a single pair of strategy or a single entry of this matrix. If we find some strictly dominant strategies, then we just keep removing them. And if we can arrive at such an entry, then we can for sure say that it is in the Nash equilibrium. But it might not always be possible that we are able to always find a strictly dominated strategy. Like it need not always be true that a strictly dominated strategy always exists. And you can probably see the reason why also. So the problem is asking us like just calculate the final payoff by the iterated elimination of strictly dominated strategies. So just identify if there are strictly dominated strategies and just iteratively eliminate them. If the process does not reduce to a single pair of strategy, so like if you don't, if at any point you are not able to find some strictly dominated strategies to remove, then just mention that the process does not reduce to a single pair of strategy. Okay, I think there is a similar question like this in the weekly quiz also. So maybe we'll just discuss this. So the strategies for the so let's just see like so there like this problem is a bit simple. Like there are just two strategies for the row player T and B. Similarly, two players for the strategies for the column player. The strategies are L and R. Two strategies for the column player which are L and R. So let's just see if there is some notion of strict strong dominance between L and R. Okay. So let's just see if L strictly dominates R or R strictly dominates L or none of these. So if the role player plays T, then okay, and we are talking about column player strategies L and R, so we'll be looking at the second entries of the tuples. So if the row player plays T, then column player on playing L gets a payoff of 0, whereas on playing R gets a payoff of 2. So if the row player had played T, then R is a strictly better strategy than L. But if the row player had played B, then if the column player played L, the payoff is 3, and on playing R, the payoff is 1. So in this case, if the row player played B, then strategy L was a better strategy than R. But if row player played T, then strategy R was a better strategy than L. So from this, like you can probably see that so neither does the strategy L dominate the strategy R, neither R dominates L. Because in one case, like if the row player plays T, then R is better. If the row player plays B, then L is better. So there is no single strategy between L and R that strictly dominates the other. So between L and R, we can't talk about strict dominance. But let's just see between T and B if there is a notion of strict dominance between the strategies T and B of the row player. Okay, so suppose the column player had played the strategy L. And now since we are talking about the row player strategy, we'll be talking about the first entries of these tuples. Like I hope it's clear. So we have to compare like if between strategy T and B, one strategy strictly dominates the other or not. Suppose the column players played this strategy, the strategy L. What happens is like if row player played T, then the payoff for row player is 1. On playing B, the payoff is 0. So T is better than B if the column player played L. Similarly, if the column player played R, then T gets a payoff of 1 and B gets a payoff of 0. So this means that again, like T is better than B. So irrespective of whatever column player plays, L or R, T is a strictly better strategy than B. This one is greater than 0, this one is greater than 0. So that's why we can say that like here T is a strictly dominating strategy over B. And this means that maybe I should just bring the answer up. Yeah. So what we do is so T is strictly better off than B. Should I bring this answer up? Yeah. So the strategy T strictly dominates the strategy B, so we can just remove this strategy B altogether. And now the payoff matrix only consists of this row. So this is the payoff matrix on removing the strategy B. So we remove the strictly dominated strategy, and now we again check. This is what we call iterative elimination of strictly dominated strategies. And now in this, we again check if there is a dominating strategy or not. So like the only pair which can be like, so we again compare the strategies L and R if one of the strategies strictly dominates the other. And you can actually see that since row player can only play T, between L and R, like if the column player played R, then the payoff is 2. If the column player played L, the payoff is 0. So since 2 is greater than 0, this means that R is a strictly dominating strategy over L. So this means that you can again remove this entry L, and you will arrive at this T comma R. So on removing L, we get the final strategy pair as T comma R. And the payoff which both player gets is 1 comma 2. And this will be the Nash equilibrium which we arrive at in the end. So this process of iterated elimination of strictly dominating strategy finally led us to something like a T comma R for this problem. And the final payoff was 1 comma 2. Okay, so I hope this is clear to everyone. If not, again, like you can ask me in chat and I'll try to explain it again. If not, if no one asks me anything, then I'll be just assuming that everything is clear. Okay, so now maybe we can move on to the sixth question. So sixth question is again about this iterative elimination of strictly dominated strategies, but it's in a 3x3 matrix. Earlier, the problem was a bit easier. It was 2x2 matrix. Now we are talking about the 3x3 matrix, and the problem says that calculate the final payoff by iterated elimination of strictly dominated strategies. If the process does not reduce to a single pair of strategy, then mention so. So yeah. So maybe we can see here, like, does there exist a pair of strictly dominated strategies, or does there not exist a pair of strictly dominated strategies? So let's just see right now. So let's just compare, like, so we'll have to compare the strategies pairwise, right? So like, let's just start comparing the strategies for the column player. Let's just compare the strategies L and M. If there is some dominance in between the strategies L and M. So between the strategies L and M, let's say like, let's see what happens. So if the row player played T, then L gives column player a payoff of 1, whereas M gives payoff of 0. So L is better than M if row player played T. Similarly, if row player played C, then if column player played L, again he gets a payoff of 3 and on M gets a payoff of 0. So 3 is greater than 0. So if row player played C, then again L is better than M. But note that if row player played T, if the row player played B, sorry, then on L the column player gets a payoff of 2 and on M gets a payoff of 5. So here 5 is greater than 2. So in this case, like, M is a better strategy than L. So note that between L and M, there is no clear, strictly better strategy. Like in some cases, like M is a better strategy. In some cases, L is a better strategy. So we can't conclude like in between both of these if there does not exist. So we can conclude that M between M and L, there is no strictly dominated strategy, strict dominance relation between M and L. And now let's check for this pair M and R. So between M and R, like if row player played T, the payoff is 0 for the column player. And on R, it's 2. So R is better than M if row player played T. Similarly, if row player played C, then again R is better than M because 2 is greater than 0. But if the row player played B, then M gets a payoff of 5, whereas R only gets a payoff of 1. So if the row player played B, then M is a better strategy than R. So in the first two cases, R was a better strategy, but in the last case, M is a better strategy. So again, we can't conclude that there is any strict dominance between M and R. In some cases, M is better. In other cases, R is better. And now let's compare this pair of strategies, L and R, if there exists any strict dominance relation between L and R. So see, like, let's see, if row player plays T, then R is better than L because 2 is greater than 1. But if row player played C, then L is better than R because this 3 is greater than 2 for the column player. So in one case, like L is a better strategy than R, whereas for the other case, R is a better strategy than L for the column player. So what this means is that, yeah, again, there is no strict dominance between the strategies L and R. Okay, so we know that between these column player strategies, there is no strict dominance relation. Let us now check for these row player strategies also, if there is any strict dominance or is there not. So suppose we check between the strategies T and C if there is any strict dominance or is there not. So if the column player played L, and now like since we are in the discussing about row players, we'll be discussing only about the first entries of the tuples, not about the second entries. So if the column player played L, okay, yeah, I don't know what happened. One guys, yeah, this was the question. Sorry for the I pressed some key and just move some. Yeah. So yeah. So we were discussing that between T and C if there is any strict dominance relation or is there not. So we can see that if the column player played L and you can see that on playing T and C in both these cases, the payoff is 1. the payoff is 1 in both these cases. So what this means is that like in strict dominance, we need that one is strictly greater than the other. But here, none of these strategies is strictly greater than the other. So we can conclude that between T and C, there is no like strictly dominated strategy. Similarly, between C and B, let's just check between the strategy C and B. So between C and B, if the column player played L, then B is a better choice than C because 2 is greater than 1. But if the column player played M, then both of these strategies give a payoff of 1, P and C. And that's why again there is no strictly better notion of there is no notion of strictly better. And so we can say that again between C and B there is no strict dominance because there is no strict inequality here. 1 is equal to 1. So between C and B also there is no notion of strict dominance. And now let's check between the pairs T and B. So between T and B, let's see if there is some notion of strict dominance or is there not. So if the column player played the strategy L, then T gives a payoff of 1, B gives a payoff of 2. So B is better than T if column player played L. But note that if column player played M, then T is better than B. In L, B was better than T, but if M was played by column player, then T is a better strategy than B because 2 is greater than 1. So we get that in some cases, like B is a better strategy, in the other cases, T is a better strategy. So again, we conclude that between B and T also, we can't say that there exists a pair of strictly dominating, like there exists a strictly dominated strategy. So we checked actually all pairs of strategies, all column strategies, and all the row strategies, and we were not able to find like any pair. Uh, so we were not able to find any pair which was like strict, in which there was strictly dominance notion. So that's why, like for this question, like the process does not reduce to a single pair of strategy. So yeah, because there is no strictly dominated strategy. So in this question, we can just answer no strategy strictly dominates the other. Yeah. Okay. So now let's go to the seventh problem. And why did I place this seventh problem here? So uh, I hope it will become clear to you in a minute. So the problem says that consider the game of rock, paper, scissors. So I hope everyone has played like rock, paper, scissors in their school times. So like the rock, paper, scissors game can be modeled as a payoff matrix also. Because like we know that rock beats like paper beats rock beats scissors, and scissors beats papers. And now we have two players which are playing the game. And if both players play rock, then no one is the winner. So it ends in a draw. So both player get 0 points. But like if one player played rock, player one played rock, and player two played paper, then paper beats rock. And if paper beats rock, okay, I think yeah, this should be in my opinion. Oh, yeah. So paper beats rock, so that's why a column player gets 1 point and a row player gets a -1 point because row player has lost. Similarly, since rock beats scissors in the rock and scissors option, like since rock beats scissors, so row player wins, so row player gets 1 point, and column player gets a -1 point for losing. So basically, a draw gives you 0 points, a win gives you 1 point, and a loss gives you -1 point. And this is how you can model the payoff matrix for the rock, paper, scissors game, right? So now the problem asks find the deterministic Nash equilibrium if it exists. If it does not, then mention so. So this word deterministic might be a bit confusing to you, but essentially what I'm asking in the problem is what we're asking in the problem is for this kind of a payoff game, does there exist a pair of strategies which is a Nash equilibrium? Like, does there exist a strategy profile out of these? So these will be like there are three strategies for the row player, there are three strategies for the column player. So does there exist? So there will be like 9 strategy profiles, 3 cross 3, 9. These are the 9 strategy profiles. So out of these, is one of those strategy profiles a Nash equilibria, or is it not a Nash equilibria, or is there no Nash equilibria? I would like you guys to like think about it for 2-3 minutes. Like, does there exist like out of these 9 strategy profiles a Nash equilibria, or does there not exist? So Deepak or Darshan, like, would you like to answer in chat, like, if there is a Nash equilibria or is there not a Nash equilibria? Okay, so actually, if you go about this, you will actually see that there does not exist any Nash equilibria. And why is the case? Like maybe we can discuss what are some of the entries. So like suppose like we check for this entry, is this rock comma rock a Nash equilibria, or is this not a Nash equilibria? Then what we can say is, okay, suppose like we check if any player has any incentive to switch or not. So you can actually always find for any player, you can find uh, an incentive to switch for the players. Like if it was a rock comma rock, then the row player maybe has an incentive to switch to a paper so that the row player wins. Like right now it's a draw, but if I change my rock to a paper, then maybe I'll be able to win. So I have an incentive to switch. Similarly, if it was a rock comma paper, this entry, then right now the paper player, the column player is winning. So column player will have no real incentive to switch as he's winning anyways. But what row player might think is maybe like he can change from a rock to a scissors so that like he'll be able to beat the paper. So this will be uh, a better. So the row player will want to switch from the rock to the scissors. So row player will have an incentive to switch from rock to scissors as his payoff will increase from -1 to 1. So that's why this also won't be an Nash equilibria. And similar arguments can be made for like all other cases also. So actually like for this game, like for rock, paper, scissors game, there will be no Nash equilibria. And yeah, like this is something we know also, right? Like because we know that in a rock, paper, scissors game, like what Nash equilibria essentially tells us is that okay, like Nash equilibria, the states of Nash equilibria are the states where what the players will actually tend to play in the end. So Nash equilibria models what the players will tend to play in the real world. And we know that in rock, paper, scissors, like there is no like fixed pair like which the players want to always play. Like there is no fixed strategy profile which the two players will play. Like it's always usually random or something. So yeah. So there is no deterministic. So out of these 9 strategy profiles, none of the strategy profiles is a Nash equilibria. Which brings us to an important observation that which I want to point out that Nash equilibria need not always exist. So a deterministic Nash equilibria. What I mean by deterministic Nash equilibria that like there does not always exist like a pair of these kind of strategy profiles which will be a Nash equilibria. In some cases, like in the previous problems which we discussed, there always existed some Nash equilibria. But here you can see that the Nash equilibria won't exist. Like, and what do I mean that it won't exist? Like, what do I mean by deterministic Nash equilibria? By that I mean like something like out of these 9 strategy profiles, none of these will exist. But actually, there's something very interesting. There's a very interesting result which will probably occur in like some later lectures. You will learn about it. So uh, there is something called a randomized or like probabilistic Nash equilibrium, and that you can show that it will always exist. But that's a thing for another day. Like, but yeah, in these like kinds of setting, like there can be cases where Nash equilibrium does not exist. And this is something which I wanted to point out. Okay, then. So I hope it's a bit clear to everyone. If so, then maybe, okay, this is the eighth question. I think, okay, so there was this eighth question and there was this fourth question which was left, which we did not discuss. So maybe I think since we have limited time, we can only discuss one problem. And like, I think fourth problem is a more relevant problem for you guys. So maybe we can discuss this one. And the last problem, the eighth problem, like I have already recorded its solution like I had already discussed its solution on the Monday 6 to 8 p.m. session. So maybe you can see the solution for that problem in that session. So yeah. So this will be the last problem of the day, which we'll be discussing, the fourth problem. And this is the problem which is a bit on the like harder side, I would say. Like not very hard, but like uh, a bit more non-trivial or a bit more interesting. Okay. So here what we have is the problem says that consider we have two nodes. Let's say one, like we call one as a source node, the other as a terminal node. And they are interconnected via root A and root B. So there are these two nodes connecting source and sink. So there are two roads, and like the cost of traveling from S to T using route A is given by the fraction of agents using the road A. So what this means is that so if there are like okay, maybe we'll discuss that later. The cost of traveling, the cost of traveling uh, using route A is given by the fraction of agents using A, and that for B is always one. So cost of traveling. So there are two routes, and like if an agent travels through route A, the cost agent will have to pay for traveling will be equal to the fraction of agents which are using A. But for B, like so basically the cost through A depends on the number of agents which are actually traveling through A. But for B, it is always fixed as one. That what you will always on taking the road B, you'll always be paying a cost of one. And now suppose there are total like n agents traveling from S to T, and NA denotes the number of agents using the edge A. So basically, like if n small a is the number of agents which are using the edge A, then the cost of traveling via route A is given by the fraction of it, like this fraction NA by n, right? Like this was what was like the cost of traveling through route A is given by the fraction of agents traveling through A. So the fraction of agents traveling through A is equal to NA by n, and cost for using B is always one. So cost for using B is one, and for cost of using A is NA by n. And now like for n equals to 3, so let's just suppose that there are three agents, like actually there are three people who are traveling from source to the terminal. Then if we formulate this problem as a game, so we can actually formulate this problem as a game, like where each player's strategy is the choice of the route it takes to travel from S to T. So what does this mean? So there are three people. So each of these three people can choose whether they want to go from S to T via route A, whether they want to take the route A, or whether they want to take the route B. So there are like two choices for each of these three people. Like so there will be kind of like total eight possible strategy profiles. Like 2 raised to the power 3. There will be eight possible strategy profiles. And now we want to see that and and each player wants to minimize the cost of travel also. Like each player will want to minimize its cost of travel. And now we want to see like out of these eight possible strategy profiles, which of these will be a Nash equilibria and which of these won't be a Nash equilibria or something like that. Okay. So I hope the problem statement is clear to everyone. So the option A says that there are no Nash equilibria for this game. So maybe we'll come to this option later. We'll try to first analyze the other option and then we'll see if there exists a Nash equilibria or does there not exist a Nash equilibria. So B option is the strategy profile AAA is a Nash equilibria. Okay, so maybe like what we can formulate here is there are three agents and Na is the number of agents using edge A. So Na can be equal to 0, Na is equal to 1, Na equal to 2, or Na equal to 3. Like no agent takes A, the root A. One agent takes the root A, two agents take the root A, and three agents take the root A. So we want to see like out of these, which of these will be a possible Nash equilibria. Right. So the strategy profile AAA, the option B says, is a Nash equilibria. And what's the strategy profile AAA mean? It means that all the three agents are taking the root A. So is this a Nash equilibria or is this not a Nash equilibria? So actually, let's just consider this. So let's just consider any of the agents. So just consider, let's say, the first agent who's taking the root A. So we know that all three agents are right now taking the root A. So the cost of the route was given by the fraction of agents traveling through A. And since there are total three agents and all are traveling through A, so cost through A will be equal to 3 by 3, which is equal to 1. So if all three agents take the route A, so cost of traveling through A will be equal to 1. And note that the cost of the traveling through B is always equal to 1. So right now all the players are paying a cost of 1. If let's say one of the player decides to switch, so even after switching to B, that player will have to pay a cost of 1 nonetheless. So in this case, none of these players will have a real incentive to switch because they will be going to a cost of 1 only. Like if they switch to B, they will have a cost of 1. And that's why this won't be a Nash equilibria. And like I think this is what we have discussed. This is also what we have written. So note that the cost of traveling through B is also 1. So no agent has an incentive to switch to B. And hence AAA is a Nash equilibria because no agent has an incentive to switch. Right? And now let's look at the third C option. C option says that AAB, ABA, BAA, and AAA are Nash equilibria. So are these strategy profile Nash equilibria? So we already know that AA is a Nash equilibria because we just discussed it in the B option. And out of these three strategy profiles, so what does these three strategy profile mean? Like they just mean that if two of the players are taking the route A and third player takes the route B, then is this a Nash equilibria or is this not a Nash equilibria? This is what we want to check. So note that if two players are taking the route A and one player is taking the route B, then the fraction of people taking route A is equal to 2 by 3. So cost of traveling through A will be equal to 2 by 3. So what this means is that the agents who are going through A are paying a cost of 2 by 3. So they won't have any real incentive to switch to B, right? Because if they switch to B, they will have to pay a cost of 1. And since 2 by 3 is less than 1, so the agents traveling through A will have no incentive to switch. And now let's consider the third agent, that agent who's traveling through B. If the agent who's traveling through B, will he have an incentive to switch or not? So that agent is currently paying a cost equal to 1. But what happens if that agent also switches to A? So if that agent switches to A, then actually now people are traveling through A. The initial two were anyways traveling through A. Now the third person also switches, and so he's also traveling through A. And so the fraction of people traveling through A becomes equal to 3 by 3, which is 1. So note that the person was initially traveling through B was giving a cost of 1. And now even after switching, he has to pay a cost of 1 nonetheless, because now the fraction of agents traveling through A increases. So that's why even so there will be no real incentive for this third person to switch also, because he'll be paying the same cost nonetheless. And so that's why this is also a Nash equilibrium, because no agent will have an incentive to switch. Okay, and now maybe we can move on to the D part. So D part says that the strategy profiles ABB, BBA, BAB. Okay, I think there's some question in chat. So Deepak, I don't think these kinds of questions maybe Deepak, maybe we can right now discuss these questions. Maybe like just these questions like which are not related to academics can be discussed afterwards or something. Like let's just for now focus on like the problem which we are discussing. Yeah. So and like just like by the way, like I'm not a, like a professor. I think I'm just a PhD student right now. So yeah. So the D option is the strategy profiles ABB, BBA, BAB, and AAA are Nash equilibria. So we already know that AAA is a Nash equilibria, but let's just talk about these strategy profiles ABB, BBA, and BAB. So these are the strategy profiles where exactly one person is taking the route A. So if exactly one agent takes the route A, what happens is the cost of traveling through A will be equal to 1 by 3 because one agent is traveling through A. So this agent, the one who is traveling through A, will not have an incentive to switch to B because on switching to B, he'll have to pay a cost of 1. And currently he's paying a cost of 1 by 3. So 1 by 3 is less than 1. So he won't have any incentive to switch. But let's just consider any agent who's traveling through B. So the agent who's traveling through B, so there are two agents right now who's traveling through B. So consider any one of the agents. So this agent is currently paying a cost equal to 1. But if this agent switches to A, then till now there were only one agent who was traveling through A, and if this agent also switches, then there will be two people who are traveling through A. So the cost of traveling through A will become equal to 2 by 3. But note that currently this agent is paying a cost of 1, and on switching, so he'll have to pay a cost of equal to 2 by 3. And we know that 2 by 3 is actually less than 1. So this agent will have an incentive to switch. So yeah. So if exactly one agent takes the route A, cost of traveling through A is 1 by 3. The agent traveling through A has no incentive to switch, but an agent traveling through B will have an incentive to switch as cost on switching to A is equal to 2 by 3. So this won't be an Nash equilibria because this agent traveling through B will have an incentive to switch. So only options B and C are correct, that AAA and AABs are Nash equilibria. And like option A is anyway incorrect because we found a Nash equilibria. So the statement that there are no Nash equilibria is false. So A and D statements are false, so only option B and C are correct. Okay, so I hope this is clear to everyone, and if it's not, like you can ask me via chat. I think we have something like 5 minutes left. I'll try to explain this problem again. So I won't be taking up the last problem, eighth problem right now because I think this problem will take a lot of time. And if you guys are curious about this problem, like I have discussed this in the Monday 6 to 8 p.m. session, which was uploaded on the YouTube channel anyways. So you can see this problem there also. But for now, let's just focus on this fourth problem. If there are any doubts, then I can take the doubts related to this fourth problem. If there are no doubts, then maybe we can also close the session. And like just for information, like I'll be also uploading today's session also on YouTube. So yeah. So mm, just making the announcement again that you can uh, watch this session also, the recording of this session also on YouTube. Okay, so I don't see any questions in the chat right now, so I'll be assuming that like this whatever we have discussed today is clear to everyone. So if it is clear to everyone, then maybe like yeah, we can like maybe we can close the session and yeah. So once again, everyone, like thanks for joining and attending the session. So hope to see you guys uh from next session onwards regularly. And note that from next week onwards, the sessions will be only on Mondays on 6 to 8 p.m. So yeah, if you want to attend the session, like just mark your calendars. So yeah, and I hope to see you guys. on Monday, 6 to 8 p.m. So till then, goodbye, guys. I'll stop sharing and you can also leave the session. Thanks for joining, guys, and bye bye.